Foundation Models for Embodied Decision-Making Agents, Part 18. This is a presentation by the lady that just got her PhD in the Autonomous Systems Lab here at Stanford, and she's talking about out-of-distribution behavior. So when robots are exposed to an environment that they weren't trained on, so when the data is out of distribution. And when you have two problems, one is the data is out of distribution and or your functionality, your action space that is possible based on your training is not applicable anymore. So what she's done, and I put all the details in the show notes, names and papers and things like that. So what she's done is she has developed a model of adaptive learning. So the idea here is that whenever you are in out of distribution, one is detect that you're out of distribution. So understand when things have changed and then learn from that. So this is fundamental, and I think I'm really excited about this presentation. It's one of those presentations that I could just sense from the beginning that it's an interesting situation. I mean, first she was very excited, and she was pretty succinct and clear of what she's doing, and to me that's always a very favorable situation. I think I want to do a podcast at some point, or an episode where I just talk about my experiences here at Stanford listening to seminars and how they differ and how intellectual capacity often correlates with the ability to explain things, but more importantly also inspire people to work on things. I think this is one of those examples where you just want to go and work and read and understand. Okay, so what does out of distribution mean? Out of distribution, again, it has two fundamental factors. One is imagine a Tesla car driving and being exposed to new types of data, right? For example, there's hail that it's never seen before, and it has to do, or it's been trained in California, and now there's ice, right? Ice. So it hasn't seen that before. So that's, think of that like data distribution, and then there's and or. So this could be as a consequence of that, the functionality of the car could be inhibited. In other words, the car can't do what it's supposed to. It can't turn right on a right turn because of the ice, right? So that will be functionality. And the way you want to mitigate that, and this is really a philosophical conversation now. What do you do with that? Like, for example, okay, one thing that you can say here is that, well, being out of distribution just means you haven't trained well enough. In other words, if you train well enough, you should never be out of distribution. For example, that's what, in my opinion, drives GPT, right? The ability to train from a huge pool of data and have unsupervised learning applied to it allows you to never really be out of distribution, because you've just covered almost every possible combination of in this case in GPT of text and the tokens that are associated with the text. So you've done all of that, and you're just, again, you can't even be out of distribution. So somebody that's well trained, when we say such and such is well trained, what we really mean with that is the person can barely be out of distribution, or Lionel Messi, Kylian Mbappe, or Michael Jordan. They can't be out of distribution within the context of the game that they're in, whether it's football or basketball. They just cover every possible situation. So that's one thing. So you can flip this on its head, and you could test the model and this brings the other question of detecting out of distribution, which is part of the PhD thesis, right? How do you even detect that? And there's a very simple example. Of course, you can say, look, if I train a model to identify characters, let's say, or numbers, right? I train a model to just identify digits, and there's 9 digits plus a 0, so we have 10 digits that we deal with. And if we now show the model a picture of a car, that's out of distribution. This model is not going to be able to predict the car. because it's been only trained in predicting numbers. And what you can do is you can, well, number one, detect, okay, this is our distribution, this is something new, and then you might actually learn. And how do you learn? You put that in your training data. You say, okay, this piece of data, this this car, we're going to put that in the training set. So next time we train, we want to have a bunch of examples of cars, and then train that against other examples of cars, and then so get better at predicting cars. And if we could build a sort of looping model here that learns how to learn, then we could actually become self-sufficient. This is, in a sense, what meta-learning is all about, and I think the transformer architecture is just the culmination of that. Because what transformers are doing is, instead of doing this learning how to learn sequentially, they just do it in one shot. They just go and say, look, we could have a combination of numbers, and we could have a combination of numbers and cars and pens and flowers, and we're going to try to learn in one shot, in a parallel way, all the possible combinations, and then be able to answer questions like, what is this, or is this the same as this, and so on and so forth. Now, again, auto distribution in this context just means that we haven't trained well enough, and we can develop algorithms and architectures that take into account the possibility of auto distribution, which is what transformers do. Or we could have a meta-learning process where we learn how to learn based on mistakes. That's really what it is. So that's in a nutshell what it is. I think fundamentally you could now, of course, go much deeper, and that's why you do a PhD in things like that, where you ask yourself, okay, how do I detect auto distribution? Because you also don't want to have false negatives, right? You don't want, false positives. Like, you don't want to constantly detect things that you think are auto distribution, but in fact are not auto distribution. And on the other hand, you could say, well, I don't really care about any kind of auto distribution data. All I care about is functionality. As long as my Tesla can drive, do I really care what data it's dealing with? But then, of course, that's a risk, because you don't want to get this to the test of you don't want to say, well, as long as I don't have an accident, I'm in distribution, and the moment I have an accident, I'm out of distribution, because you don't want to have the accident in the first place. So you have to find ways to a priori make sure that these things don't happen. I think where this culminates, in my opinion, is in simulation, right? The best way to deal with auto distribution is to have as many shots on goal as possible, to have as many try and errors as possible. This is, I don't know any other way. I mean, there's probably better, maybe approximations of that, shortcuts, things along those lines. But I spoke about Dieter Fox yesterday, head of NVIDIA's robotics research, and also UW professor at the Paul Allen School of Computer Science and Engineering. And I think that's where NVIDIA is going. That's where Tesla should be going, which is you want to try to go into the realm of simulation, because you want to cover as much auto distribution as possible. And the solution to that problem of capturing as many auto distribution examples as possible, in my opinion, lies in simulation. This is another analytical way to derive to the same conclusion that Dieter Fox is arriving to, that Jitendra Malik is arriving to, Peter Abil, Sergey and others. And that is, look, how do we make sure that we cover as much auto distribution data as possible and auto functionality situations as possible in the robotics realm? And the answer is, we build a multimodal, transformer-based robotics model that starts with image data from the real world. So I take a picture of a road, and I take a picture of rain, and then I feed this into a Gen AI model, like something along the lines of a visual transformer, that then is able to generate many, many more trajectories of rain. You could have an example. You could have a Monte Carlo distribution of rain, starting with very heavy hail all the way to the lightest possible rain that you can find in a high plateau desert. And you can have that car drive on the road with all these types of rains. You could have a situation with the driest possible road you can find, maybe in the Atacama Desert, all the way to the wettest and most slippery, and then coldest and hottest, and so on and so forth roads that you can simulate all of this in a generative AI type simulator, and you could have some Q-learning type algorithm that actually drives through all those scenarios, and therefore covers so many possibilities that there's almost that the chance of out of distribution gets minimized. So you could minimize for out of distribution. You could have a learning architecture that is optimized to minimize for out of distribution. Now, in order to do that, you'll have to, of course, have a sense for what is possible, and then simply generate enough trajectories so that possible gets covered almost entirely. And the possible can be approximated in actually trying to really understand what is, it would be a physics model. So in the case of rain, you would have a actual physics model of rain and just cover excuse me, all the possible variations of rain. Or you could just have a data-driven model which says, look, I don't even care what's possible. I'm just going to start with an extreme case over here, and then go very gradually over there and cover all possible occurrences of H2O in the atmosphere, and even change the atmosphere and have rain on Mars and rain without gravity and all kinds of things. Once we're in sim, once we're in the virtual world, our opportunities are almost endless. They're not endless because we're confined by Moore's law, we're confined by things like memory and compute and things like that, but that's okay. I think we can totally handle that at this stage. There's probably a stage at some point where we're going to say, well, we need to do better, but that's not the problem right now, because right now we're actually constrained with real world scenarios. So we have to actually, let's say, drive the car in the real world, which Tesla has found a way to circumvent by using the fleet and using the camera system. So we spoke about this in the past. But again, I guess to summarize, this out-of-distribution problem is really a very interesting question. It's one of those fundamental questions in AI, which is, okay, look, we have, what does it mean to be out-of-distribution? What does it mean to have a model that has a lot of out-of-distribution data or functionality? Well, that just means the model is not trained well enough. And in other words, how can we minimize out-of-distribution? Well, we can find better ways to train the model. And then what does distribution mean? And then the distribution itself is changing also. And then, we can also ask even more fundamental questions, which is, well, our distribution depends on what we see. And if we get better let's say better resolution, if we can get into electron microscopic type resolutions, then all of a sudden the data is completely different. Now, does that really matter for a robot that is driving around in the real world? Maybe not. But it certainly matters for maybe a robot that is doing surgery. So in a sense, observations are theory laden. Theory decides what we see. Theory decides what we actually consider distribution. So this is a referential question here. It's not like we have a given distribution of the real world, and now we humans just try to approximate that. The distribution of data of the real world changes with our knowledge. For example, having a car that drives in rain depends on our understanding of rain. And we might as well have a very different understanding of rain on Mars, because their rain is maybe something else. So it requires more theory. So this is an ongoing problem, I think a very interesting problem, but from an engineering perspective, I think the solution is to minimize out-of-distribution by having the most appropriate training given the goal of minimizing out-of-distribution. And that is, in the text realm, has been the success or the solution to that is actually the transformer architecture, because you can do many iterations of different types of combinations of words or tokens in one shot in parallel, and therefore you can minimize auto distribution. And in the robotics realm, that's going to be a little more difficult. And that's why we believe that the solution in the robotics realm will be in simulation. Thank you.